In this video, we're going to go through the full 5-step process for a chi-squared test of independence. So this is an example, real data. I got it from an episode of Freakonomics, but they were trying to figure out whether more choice was always better. So a researcher set up a tasting booth for different jams in a grocery store, and she alternated the size of the choice set. So sometimes the booth would have just 6 different jams to choose from, and sometimes it would be a large choice set with 24 different jams to choose from. And she looked at a couple of different outcomes here. So we're going to analyze these data in JMP, but I wanted to start off by showing how the data are formatted here. So this is different from what we've seen previously. Earlier, we've seen data sets like this, where we have a whole lot of rows and every individual has their own row in the data set, recording the different categories that they fall into. But this is different because instead of every individual having their own row, the rows are just each combination of the categories, and then for each combination, we have a count. So we're still going to use analyze fit y by x to analyze these data, and we're going to start by looking at the association between the size of the choice set, that's our explanatory variable, and whether or not the customer stopped at the booth. But we don't want to stop here. We do want to include the counts somehow, so the counts go down here in the frequency box. So this extra step is only necessary if the data are given in a table like they are here. So we can see the output includes a mosaic plot, a contingency table with a lot of different percentages in it, and then also the output for the chi-squared test. So whenever we're doing a theory-based test like this, we want to start off by checking our assumptions. So first, let's just make sure that we've got the right type of data for a chi-squared test of independence. So a chi-squared test of independence is when you have a categorical response variable and it's being observed in 2 or more groups. So we've got a categorical response, whether or not the customer stopped, and 2 groups. We've got the choice set, either small or large. So this condition is met. We also want to make sure that we have expected counts of at least 5 in all of our cells. So if we want, we can get JMP to do these expected counts for us. That's one of the options in the contingency table here. So I'm actually going to get rid of these percentages. I'm not using them right now. And I'm just going to look at the expected counts. So notice the little label in the corner. That's telling me what's given in each cell. So each cell has the count and the expected count in it. So I can see by looking at the JMP output here that all of my expected counts are way bigger than 5. So if I didn't have JMP and I wanted to check the conditions quickly, I might just check the smallest expected count, right? Because as long as the smallest expected count is bigger than 5, then you know you're good to go. So remember, the formula for expected counts is the row total times the column total divided by the overall total. So if I just wanted to check the smallest one, then I would just look at the smallest row total. So that would be 157. And then the smallest column total, that would be 159. And look at that out of the overall total, which is 320. And I end up with an expected count of 78.01. So that's my smallest expected count, and it's much bigger than 5, so we're good to go. And that's just the number from here. Ideally, we'd also like to have some kind of randomization, such as random selection or a randomized experiment. It doesn't really say that we have either of those here. So the fact that it's not random selection, right? If we think about how these data were collected, they were at a single grocery store, so it might be a little bit risky to generalize to other grocery stores. We also don't know that it was randomly selected in terms of like the time of day. So maybe the customers who came while this booth was set up might be different than the customers of the store overall. So that would be something to be concerned about, something we'd need more information for. We also might be concerned about confounding, right? Because this seems to be set up to show a difference between small and large choice sets, right? I think ideally the researcher would like to say that the choice set causes a difference in the number who stop. But to do that, I'd want to know a little bit more about how she alternated the choice set. So see if you can think of a situation where you would end up with confounding based on how the choice sets were alternated. Pause the video for a second and see if you can think of one. So we're interested in whether the size of the choice set affects whether or not the customer stopped, and we want to know if there are any possible confounders. But remember, for something to be a confounder, it has to be linked to both the response variable and the explanatory variable. So one potential confounder that I thought of would be like the day of the week. So for example, what if she set up the small choice set on a weekday and the large choice set on a weekend? Maybe people are more likely to stop at these kind of booths on the weekend because, they have more time, they're not in as big of a rush. So maybe in that case, it wouldn't really be the large choice set that was drawing them in. Maybe it was just because they had more time and they could check out new products or whatever. So if you had something like this where the size of the choice set was associated with some other variable, then that could possibly lead to confounding. So hopefully there was some sort of randomization involved, or at least she took care to make sure that there weren't any obvious confounding variables. Okay, so let's state our hypotheses. And I'm just going to state them in words this time. So when you're doing a test of independence, the null hypothesis would be that there is no association between the variables that you're considering. So in this case, no association between the size of the choice set, that's our explanatory variable, and whether someone stopped, that's our response variable, whether the customer stopped. So in other words, the null hypothesis would be saying that it doesn't matter which choice set people see, that they're equally likely to stop at the booth. It doesn't have to be a 50-50 chance of stopping, just that the chance of stopping is the same regardless of which choice set they saw. That doesn't seem to be what's going on in the sample, right? In the sample, it looks like the larger choice set leads to people stopping more often than the smaller choice set, but it could be that this is just random chance, right? We wouldn't expect it to be perfectly even in the sample, even if there were no association, so maybe that's what's going on here. Maybe choice set really makes no difference, but the large choice set had more people stop just by random chance in this sample. The alternative, the thing that we're trying to prove, is that there is an association. And I'm not going to write it all out again, but that there is an association between the size of the choice set and whether the customer stopped. So we've talked about several different options for comparing groups, things like difference of proportions, relative risk, odds ratio, but none of those are a test statistic. So a test statistic has to be standardized in a way that it shows the strength of evidence, not just the strength of association. So we've seen things like a T statistic, an F statistic, and now that we have categorical data, we're using a chi-squared statistic. And just as a quick reminder, remember the chi-squared statistic works by comparing the observed and the expected counts, looking at the difference between them squared over the expected, and you would do that for each cell and then sum them all up. So I'm not going to write this whole thing out since we have JMP to help us, but let me just do a couple cells. So like if I start with the first one in the table, the observed count was 63. The expected count was 78.99. Take that and square it over 78.99, the expected count again. And then I'm just going to do plus ... and skip to the last cell. So in the last cell, 65 was the observed count. That's the actual data. Minus 80.99, that's what we would expect if the null hypothesis were true, if there were really no association. And then divide by the expected count. And then I'm going to get the chi-squared statistic from the output. So this formula that we've been using is called the Pearson chi-square. You can actually mark out the likelihood ratio. We won't use that one. That's a slightly different formula. So our chi-squared statistic for this data is 12.790. That's what we get from the output. This is using that theory-based chi-squared distribution, right? So without even doing a simulation, we can get an idea of what values of the chi-squared would occur by random chance. But remember, there's different versions of the chi-squared distribution depending on what your degrees of freedom are. So our degrees of freedom for this one are going to be the number of rows minus 1. So in this case, we had 2 different rows for the small and the large choice set. So rows minus 1 times the number of columns minus 1. And here again, we have two columns for whether they stopped, yes or no. So 2 minus 1 again, and we end up with a chi-square distribution with 1 degree of freedom. And I could use the chi-square distribution calculator and jump to find this, but I'm just going to take the value from the output. So up here where it says probability greater than chi-squared, that number is the p-value. So we're going to get 0.0003. The p-value is 0.0003. And the reason it says probability greater than chi-squared is this is saying what's the probability of getting our chi-squared statistic, 12.790, or greater or more extreme if the null hypothesis were really true, right? If there were really no association between the size of the choice set and whether the customer stopped. And in this situation, it would be pretty unlikely. If there were no association, it would be unlikely to get a chi-squared statistic as large as ours. So because our p-value is so small, we're going to say that we have strong evidence. And we're always looking for evidence for the alternative. So strong evidence that there is an association, and I'll put this in context, that there is an association between the size of the choice set and whether a customer stopped. So the chi-square statistic itself just says that there is an association. It doesn't tell us much about what that association looks like, but we could get that information from looking at the mosaic plot, right? We can see that the large choice set has people more likely to stop than the small choice set. If we wanted to calculate those probabilities exactly, we could use the row percentages. So row percentages shows for each choice set, look at the percentage who stopped and didn't stop. So we can see about 40% stopped when they saw the small choice set, about 60% stopped when they saw the large choice set. We could also use other ways to put those numbers together, like the difference of conditional proportions, or the relative risk, or the odds ratio. So all of the stuff we learned about strength of association, we could use as a follow-up to give more description. But this isn't exactly the end of the story because we also care about whether or not they ultimately made a purchase, right? Not just whether they stopped at the booth, but whether they made a purchase. So everybody who stopped at the booth was given a coupon for this product, and that was just to allow the researcher to track their purchases. So if a customer stopped, there's two different options. Either yes, they redeemed the coupon, or no, they didn't. And then NA is for people who didn't stop at all, right? Because if they didn't stop, they didn't get a coupon, and so they couldn't redeem it. So in terms of coupon redeemed, there's actually 3 different outcomes that we could have. Either they stopped and they redeemed the coupon, they stopped and they did not redeem the coupon, or they didn't stop at all, so there was no coupon to redeem. And I set up a Google form to let you finish this analysis on your own.